Hey everybody. So today we're going to go over the homework and quiz for this week. We'll start with the homework. The first homework assignment was this new data set. And you were asked to analyze the relationship between two variables, specifically using Twitter and employment status. So you've done this a few times, or using different sorts of variables, you've done this sort of analysis. You just go to Analyze and Fit Y by X, drag your two variables, and it does a lot of the work for you. So employment status, and do you use Twitter? And because we're talking about dependence, it doesn't really matter which one you label as the response and the factor. I would just read the question to be clear. If there's one that if it's worded in such a way where one of the variables has an effect on the other, make sure that the variable that they're labeled appropriately. So the variable having an effect is your X variable. The variable that's receiving the effect is the Y variable. But in this case, the wording was ambiguous, so you could flip these two around if you like. So we'll go ahead and do that. And it does pretty much all the work for you. It does the EDA, and it does your contingency table. I'm not a huge fan of the way that they did it. I would change it. And it does your chi-square test. So for EDA, I do think a two-way frequency table like you see over here, also known as a contingency table, was the way to go. But notice they have 4 different metrics in each cell. There's the raw count, the percentage of the total, the column percentage, and then the row percentage. I would just have one of these metrics, and I think it's kind of up to you which one you want to use. I think the count is useful for answering the question of should any categories be removed, because if the sample size was low enough, and this is something I didn't mention in my lecture, but if the sample size is too low in any cell, you're not able to make an accurate, the chi-square test is no longer valid. You need a sample size of at least 5 in 80% of cells and at least 1 in all cells. You don't need to memorize those rules, but that is an assumption of the chi-square test. You need sufficient sample size in each cell. So I think that's a valid choice. Percent of total I think is a little bit less informative because it's a little better than counts for interpretation, because you can see how many people fall into each. But I would probably do percent of column or percent of row because it's easy for me to read. So here I have column percentages, right? So when I add these all up, it adds up to 100%. So I see among people who don't use Twitter, they're pretty evenly split between employed and not employed. And then you have 12% here. Or you could go the other way around where you do row percentages, and now it adds up to 100 row-wise. So this is, again, just some EDA to get at the question. And looking at this EDA, it looks like the people who are employed and the people who are not employed use Twitter at very roughly the same rates, but there does appear to be a difference among people who are employed part-time. And there's all sorts of reasons you could come up with for that. I think this is the best form of EDA. What you have above here is the mosaic plot, which I'm not a huge fan of. One student did submit a great interpretation of it, but I think it's harder to read than a table while conveying the same information. So it's just like visualizing like the relative size of each of these cells in the table. So I was really looking for the two-way frequency table, but some of you did other things which were great, like side-by-side pie charts were great, side-by-side bar charts were great. If you did use a bar chart, I think a stacked bar chart is a little easier to read than when they're side-by-side. So just something to consider moving forward. The other thing I wanted to talk about with this was the null and alternative hypothesis. A lot of people wrote it in terms of mean. But remember, both of our variables, the response and the explanatory variable or outcome and X variable, are categorical. meaning there is no mean. You can't take a mean of this sort of data. What does it mean, right? Like, to use Twitter, your response is either no or yes. You could kind of do like the percentage of yeses is a sort of mean, but like especially on this variable, it really doesn't make sense to take a mean when you're dealing with categories. So there are no means, and I did have a slide on this in the lecture where I stated the hypotheses. And with the chi-square test, it's kind of like ANOVA in that you're just generally looking for a difference between the groups. In this case, as it relates to independence. So you're just generally looking, are these variables related? You don't specify any means, you don't look into particular categories, you just say overall, is there a relationship between these two variables? Just like in ANOVA, you say overall, are any of these groups means not the same? I'm not saying which ones in particular, that's where you get into multiple comparisons and multiple t-tests, but to start, you just want to know, is there a difference across groups? So your null should have been that the variables are independent, because your null always includes like the equality. And then your alternative, on the other hand, is not your null, and you want to make sure you cover all other scenarios. So if they're not independent, then they're dependent, right? That covers the whole range of possibilities. It's one or the other. Those are mutually exclusive events, to cover another concept we learned when we were talking about probability. So that's what your null and alternative should have been. And then they did the math for you. Some of you calculated the chi-square statistic by yourself, which was very well done and very impressive. There were 6 cells, so it took quite a bit of time, because first you have to come up with the expected table, which we talked about how to do, using the row times column total divided by the grand total for each cell, and then taking the differences, squaring them, dividing by expected, and then summing up all of those quantities gives you your chi-squared statistic, which ends up being about 9.7. There's 2 different ways to do this test. Don't worry about what those are right now. I'm actually not sure off the top of my head, to be honest, what the distinction is, but they do yield very similar answers. And then you can see, and this was another point I really want to emphasize, because you should definitely know this by now, the p-value is far less than alpha, right? Alpha is 0.05, and this is 0.007, 9 or 8, depending on which of the tests you use, which is less than alpha. And when p is less than alpha, you do reject your null hypothesis. So remember, our null was that they were independent. So therefore, we conclude there is some relationship. Another point on the conclusion is some people said something like, Twitter use affects employment, or the other way around, employment affects Twitter use. Remember, we're not getting at causal inference. We're simply testing if there's a relationship between the variables. We can't say anything about causality. That's another topic for more advanced courses. Right now, we're just talking about, is there a relationship? We don't talk about if there's an effect or the direction of that effect. There could be a lurking variable, there could be a confounding variable, which we've talked about before, contributing to those effects, so we don't want to draw any conclusions like that. So anyway, this homework was pretty easy if you followed those steps, and some of you really went above and beyond and did great work on this homework. And now I want to talk a little bit about the quiz. So let's switch to Excel. This is the data that you were given for the quiz. So very quickly, I'm going to convert it to cells. I've been doing this in Excel, but you could use a lot of other programs as well. I just think this is one of the more accessible programs for people to follow along. So here's our data. And we want to calculate a confidence interval. So the first thing, what's your point estimator? We want to know the population mean. What's a good estimate for the population mean? The sample mean, right? So that's pretty easy. We just take an average. Here's our point estimator. And we know the general form for our confidence interval is the point estimator plus or minus our margin of error. And our margin of error is made up of 2 pieces. The first piece is, well, I guess the order doesn't matter because it's multiplication. So one of the pieces is the critical value of the distribution of your point estimator, and the other portion of your margin of error is the standard error. I think there was some confusion just having met with students about how you calculate standard error. It is a little different than standard deviation, and it does vary based on your statistic. But for mean and for proportions, which were the two examples we used when making confidence intervals, you just take your standard deviation and divide by the square root of n. So let's go ahead and calculate the standard deviation. There's two ways you could do this in Excel. You could actually use the standard deviation function. Just make sure you pick sample if you do, because remember, you divide by n minus 1 as opposed to n in the sample versus in the population. Or if you wanted to do it the longer way, I'm going to insert a column here. I'm going to label this as my mean, and I'm just going to label this as my deviations. And it's good practice to do it the long way, even though in the future you will be plugging it into statistical software most of the time. So you just take each of your data points and subtract your mean. I'm going to sticky that so that it remembers it as I drag. And these are all my deviations. But you notice some are positive, some are negative. What I really want is my deviation squared. So let's do that. Deviation squared. Okay. So let's do that. Equals. So now I have all my squared deviations. To get my standard deviation, I'll write it down here. And I'll put an S to be clear that this is the formula using sample. I just sum these all up and then divide by n minus 1. I know n is 12 because I counted this data before, but you could also use the count function if you're not sure. Minus 1, and wrap that in parentheses because the order of operations will mess you up. Because if you don't have the parentheses, it's going to divide by count and then subtract 1. Or actually you want to divide by the quantity of the count minus 1. So that gives us the standard deviation, and let's just do a quick check to make sure that was correct. So had I used the formula, I would have gotten hopefully the same answer. Oh no, so we made a mistake. Let's see what happened. We took this, we forgot to take the square root. That was a silly mistake. So that's the variance, what we just calculated, and then we want to take the square root, and now we get the same answer. Okay, good thing we did that quick sanity check. Or that was not a sanity check, to be clear. That was a thorough check, because we got the same answer two different ways. And so now we have our mean, we have our standard deviation. To get our standard error, all we do is take our standard deviation and divide by the square root of n, which you may remember is 12 rather, because there's 12 data points. 11 was what we divided by when calculating our standard deviation, because you divide by n minus 1. But in this case, we're going to divide by the square root of 12. And if you don't remember, you can use the count function as I mentioned before. And I wonder if Excel, okay, so this is our standard error, and I wonder if Excel has a formula for standard error. Doesn't look like it. Yeah. But it's easy enough to calculate on your own. This is our standard error. Now the last piece for our margin of error, right? We have our point estimator. I'm going to highlight what's important for our confidence interval. So the center of our confidence interval is our point estimator, the sample mean. And we're going to add and subtract the standard error multiplied by our critical value for the appropriate distribution. And a lot of people made a mistake here. I shouldn't say a lot. It wasn't the majority of the class, but quite a few people got confused here, understandably, because in all the examples we did in the lecture, we use the z-distribution. But in this case, I don't think it's a good idea to use the z-distribution. I want you to take a minute and think about why we should not use the z-distribution here. And to give you a hint, what's the notable difference between this data and the examples we did in lecture? So there's only 12 data points here. So yes, the central limit theorem says that your sample mean is normally distributed as n becomes larger. And the rule of thumb for that cutoff is 30 data points. Unfortunately, we're not at 30 here, right? We have 12 data points. If you mouse over them, it tells you right down here, there's 12 data points. So because we haven't hit 30 yet, a better distribution to use is the t-distribution. And you'll remember the t-distribution varies based on the number of data points, or in turn, the degrees of freedom. So in this case, what we're going to do is we're going to do t dot inverse. So this is like the opposite of the normal t function. The normal t function takes a value, returns the probability. Or I think it's t dot dist. Yeah, I'm sorry, t dot dist returns the probability of, you know, the value you supply and everything less than it, or if you do t dot dist right tail, everything to the right of it. But in this case, we're going the other way around, so that's why they call it t dot inverse. I actually think R's notation is a little better and more common in other languages. What they do is they use P for probability and Q for quantile. So probability we know is like the area to the left or right of your point, whereas quantile, what they mean when they use Q is it's the value of that distribution. So you can go back and forward. So if you want the probability, you supply the quantile, you get the associated probability. If you want the quantile, you supply the probability, it gives you the value. So in this case, they use inverse. You know, every language is a little different. So what should I put for probability? Not 0.05, because remember my confidence interval is going in both directions. So I want to take my alpha and divide by 2. So I want 0.025. And then if you didn't remember that the t-distribution needs the degrees of freedom, no worries. The function tells you right here, you also need to give me the degrees of freedom because that's going to affect the value. So what is the degrees of freedom? We know it's 11, but just for practice sake, we're going to do count of my data minus 1, which will give us 11 anyway. And we see that the critical value it gives us a negative number, which doesn't really matter in a confidence interval because you're both adding and subtracting the margin of error, but it's 2.2. However, if you had used the z-distribution, you would have gotten 1.96, and you would have gotten a more narrow interval because you were overly confident in the distribution that your point estimator was distributed. And we know from past lectures that the normal distribution is more narrow in the tails than the t-distribution, which has fatter tails. And it approaches the normal distribution as n increases. But here with n being so low, we get pretty different answers. So now to get our margin of error, we simply multiply these two things, and we've got our margin of error. I don't like the negative sign. I would write it as a positive number, but let's leave it as negative because it's not going to matter anyway. Now to get our lower bound, we're going to take our mean. Normally we'd subtract, but because it's negative, we're going to add our margin of error. That's the lower bound of our interval, and then the upper bound, right, is going to be the bigger number. And so this is the range of values that we would consider. And the reason I wanted to teach you guys about confidence intervals, I guess, is two things. First, they're like very commonly used, but also I mentioned in one of our very first lectures that you don't just want to report your statistic. You want to include a measure of uncertainty around it. What's the range? That's much more informative and it's better practice. So while the mean 8.98, let's just say roughly 9, does give you information, this gives you much more information. It's somewhere, I'm 95% confident that it's somewhere between 8 and 9.8, or 8.16 and 9.8. So you're just providing more information this way. And to be more clear, that's still not the interpretation that I would give for a confidence interval. I like the interpretation we talked about in, I guess, lecture 2 days ago now. Because I'm going to post this tomorrow because I extended the homework for a couple people and I want to make sure that they complete it on their own before this video is available. So the way we explained this in the lecture 2 days ago was that Should you repeat this entire process from start to finish? Collect your data, calculate your mean, your point estimator, your margin of error, add and subtract. If you repeat this process many, many times, 95% of the intervals will contain the true population mean. So is the true mean between 8.1 and 9.8? It could be, but there's also some chance that it's not. So that's the interpretation behind a confidence interval that I want to stick to. I know it's more verbose and more to think about, but it is a much more accurate way to describe it. Because I think a lot of people get thrown off when you say things like, I'm 95% confident it's in there. What do you mean? It's either in there or it's not. So that's a much more accurate interpretation. So anyway, that was it for the quiz. There was one other question on the quiz, which I'm going to go ahead and change the grading for, because I realized the question was a little ambiguous. It was about someone named Colby was looking at comparing stock prices or the performance of various funds versus the S&P 500. So right away, we can rule out a couple of tests, right? Chi-squared is not appropriate because we're not talking about categories. We're talking about performance, specifically average return is the metric for performance that was mentioned. So we're talking about means. We can rule out chi-squared. We didn't talk about F-test, and nobody put F-test, which was good because that was not something we even discussed. And then there was ANOVA and t-test remaining. And I think both of those are valid answers. Some people, and thank you for reaching out, those of you who did, put ANOVA on the basis that he's comparing many funds at once. And ANOVA lets you compare multiple means. Whereas I had anticipated t-test to be the right answer because I thought he'd compare one fund at a time. But really, they're both valid techniques for comparing means. They can both compare two means. So even if he was doing one at a time, ANOVA would work. But as you know, with ANOVA, when you do multiple comparisons, right, it tells you there's a difference. It doesn't tell you which pairs are different. So then you have to further do t-tests to identify which of those pairs are different. So I'll correct that. If you put ANOVA, I'll make sure you get credit because that is a valid response, absolutely. And good catch, those of you who reached out. So that's it for the homework and quiz, and looking forward to covering regression next week. It is a more involved topic. We'll be covering a lot of material, and hopefully you'll find it helpful in your projects, or at the very least interesting. It's definitely one of the more powerful tools in statistics that, through a lot of modifications and enhancements, is used in various ways. So I think you guys will really enjoy that topic. Thank you.